Okay. So we're going to continue with not centroids, moments of inertia. Yeah, if you were not here yesterday, there might be a hand up by the printer still. If I pull that out. I just got an email from CSUMB that they're considering a mechatronics engineering program. They have no engineering over there, which seems kind of interesting. Anybody be interested in going there? It'll be a while before they get it started. Kind of nice to have, not have to travel. A lot of people commute up to San Jose. I mean, it's a good school though, San Jose. So. Another thing we're doing, which you might be interested in, is we tried to set something up last summer for this. It was going to be kind of like an intensive design and prototyping activity, and it looks like we got to go ahead for doing it in January. And I think we'll have to pin down the dates, but it'll probably be like January 7th to the whatever, 2 weeks after that. And it's basically something that we've been bouncing around the idea that, well, actually we're doing, like for the intro class, we got a small grant to kind of spend 5 classes in the sculpture lab. So we can use the makerspace type tools they have there. They've got laser cutters, plasma cutters, 3D printers, lathes, drill presses, mills. So anything you want to make, you can kind of make over there. And we've been tossing around the idea of a mechatronics technology program. Doesn't look like that's going to work because of the requirements for employment. It's supposed to be a 2-year program where people just get, entry-level skills. Non-engineering, no prereqs. But instead, I think we might be moving some of that stuff into engineering as sort of a like almost a work experience kind of thing. And it's not really a class yet. It would be, it's going to be funded by STEM Core, which is a cohort-based computer science program that we got funding for a couple of years ago and didn't really utilize the funds, so they're actually allowing us to spend it on this. And you could basically join for free. The idea is the cohort students in computer science would get, it's first priority seating, but then if there's extra room, which I'm pretty sure there will be, engineers could, you all could be invited to participate in that. And we're going to basically sort of train people in how to use CAD. If you've taken the engineering graphics class, you'll all be pretty good at that. But also using the tools to construct stuff. And then we're going to be bringing in like professionals from the local industry to provide you project ideas. And you would have basically 2 weeks working 6 hours a day in the lab to create a prototype of something that would be useful for industry. So it kind of ties you to the workforce, gives you career experience, which you can put on your resume. And then you also get exposure to some of the local businesses, which if they, like what you do, maybe it might turn into an internship later. Of course, those are always hard to make work, but this is the idea that we've been thinking about would be kind of useful for people. And eventually we would open it up, I think, for anybody to kind of do this without any experience, just to kind of get people exposed to what the, what the design and construction process is. It's really fun kind of working in the makerspace and putting stuff together. So, yeah. It is a makerspace, but it's not like available for anybody else. You have to take the Art D7A class, but you can take that in the spring. And, sorry? Wait. Oh, well, I mean, yeah, so Gary got a lot of donations, the sculpture chair. And he wants to make it available for everybody, but it's in the sculpture department right now, which actually is kind of nice. They really know how to make anything you want. And so the odd thing is, we wouldn't really be able to have, that whole sculpture department is where they used to have the engineering program, and they used to have all those tools for engineers to use, and then they closed it down. There aren't really, opportunities to use that so much in engineering, but we can use, we're trying to figure out ways of bringing that into our program. So this is sort of one of those ideas we've been thinking would be useful. But it's basically everything you would want in an engineering makerspace. It's just in the art department. Sorry? Yeah, and that's what it is. It's really sophisticated. If you haven't been over there, it's pretty amazing. And this, you wouldn't have to, eventually it will be a class, but right now it's just going to be it's like a contract ed thing. So you would just be invited to just go there for free. Yeah, we already got a few interesting product ideas from local businesses and stuff. So I'll give you more information about that. But if it's going to be intensive, kind of 2 weeks focused, getting it done, and it's over in January, like probably the 7th, starting the 7th, 2 weeks of that. So if that interests you, keep that open in your calendar. I'll have more information about that later. So to continue, we are doing moments of inertia. Any thoughts about moments of inertia? It's weird, but it's really just calculus, certain type. You've done all these kind of things before. It's not too different from what you've been doing in calculus. And we solved a few problems together. And we learned how you can do like vertical strips and horizontal strips and all that stuff. There is this, I don't think I put this on your handout. Is this on your handout, the group problem? It is on your handout? Good, because you need more exposure to this. So for this one, we're supposed to solve for Ix and Iy. Iy is going to be on that page. And you can do both of those with a vertical strip. And remember, there were these two different ways of doing it, right? You could do the, so actually, just as a review, what were the two formulas? What's the formula for Ix? If you have a horizontal, let's start with a horizontal strip. If you're doing a horizontal strip, what would the formula be? The integral of y squared dA, right? If you're using a vertical strip, what's the formula? No, it's not. This is a vertical strip here. So there isn't really a single y for this material, for this strip, right? This strip is distributed across y. Remember what the alternative formula is if you got a vertical strip? Sorry? Nope. Yes. Instead of focusing on a dA and how far that is from the axis, since you can't really do that for a vertical strip, right? Because that vertical strip has material that's at different distances from the y-axis, right? But we found that the moment of inertia of a rectangle about its base is it's 1/3 the height cubed times the width base, right? So, and that's sort of what a differential Ix is. So you can think about this from a differential Ix point of view, and that's going to equal the integral of 1/3 of y cubed dx. Okay, likewise for Iy. And so these are the four formulas you'll really need to have down. You got to practice doing them both ways and show that you can get the same answer both ways. We'll do these tomorrow in the practice session, but it's really important. So, and then Iy is with a vertical strip would be the integral of x squared dA, right? And with a horizontal strip, it would be what? The integral of 1/3 x cubed dy. But the horizontal strip has to have the base on the y-axis. So here, this problem, can you do a horizontal strip for IY? No, because the horizontal strip doesn't have a base on the y-axis. It's not connected, right? You see what I mean? If you're talking about a horizontal strip, does it touch the y-axis out here? It's offset from the y-axis. Okay, so you can't do this formula. The base has to be on the y-axis, and this guy has to have the base on the x-axis. Right, that's the requirement. If you did do the formula of x cubed dy for this one, what you would be calculating is a moment of inertia for this shaded area right here. You know what I mean? If you did x cubed dy, if you took this x and cubed it dy, then you're actually sort of assuming that it's actually this little diy as opposed to this one, which is what you're trying to do. Could you a minus that value? No, because it's all this cubing is going on, right? This is the, it's not like the centroid is, you could do it for centroids, but you can't do it for the moment of inertia. Because, each of these little infinitesimally small d areas is multiplied by x squared when you do the integral. And so it doesn't work out that way. You can't just take 8 minus for that part. So those are your options, right? So solving for ix, well, I'll start solving for ix, so you're not helpless. So what do you want to do? Well, if you're doing a vertical strip, which formula are we going to use? 1, 2, 3, or 4? Yeah, formula 2. With the vertical strip based on the x-axis, that's what we got set up there, right? And we know that y cubed equals x, so y is the cube root of x. And so we're going to say, okay, ix equals the integral of 1/3 y cubed dx. And it just happens to be that in this case, y cubed is x, so that makes a really nifty integral because, and we're going to integrate this from 0 to 8, right? And, sorry? Pardon me? Yes, so in this case, we can replace the y cubed with x. So we're just going to integrate 1/3 x, or take the 1/3 out, integral of x dx. And that's going to equal x squared over 6 from 0 to 8. And that will equal 10.7 inches if you would do the math. Suppose you wanted to do a horizontal strip. Could you do a horizontal strip to find ix? Victor's nodding yes. The answer is yes, you can, right? The thing is, so that's with formula 1, right? And but formula, oops, sorry, that's formula 2. Formula 2. Formula 1 says ix is the integral of y squared dA. And if you do a vertical strip, that's what you're going to get. In this case, your dA is going to be this distance. What distance is that? Dylan, you said it already. You could start with 8 minus x, or 8 minus y cubed, right? And it has a thickness of, anybody? dy, right? So it's the integral of y squared times 8 minus x dy, or actually, let's just plug that in, 8 minus y cubed, cut to the chase, right? And what are the limits of integration from? 0 to 2. Now it's no coincidence, but these are completely different integrals, completely different, you know, integration limits, and yet you're going to get exactly the same answer either way you do it. And Dylan's going to check it for us. I'm not going to bother doing the integral for you, but Dylan will do it and report back to us because I want to move on forward. Yeah, feel free. And but we got to do these composite ones too, which are kind of tricky as well. And so I have a lot else to talk about. Solving for IY, you know, with this strip, let's just write the formula here and just move on because I'll give you the answer. You can kind of see if you can prove it. IY is with a vertical strip. So this is going to be formula, what's that? Formula 3. It's going to be the integral of x squared dA. And in this case, the dA is going to equal, well, the height is going to be yeah, it's y, which equals x to the 1/3, right? And the thickness is going to be dx, right? And so it's going to be the integral of x squared times x to the 1/3 dx from 0 to 8. And that should equal 307 inches to the 4th. So you can try your hand at the integration and see if you can get that answer. Okay, and one more attention quiz. When determining the moment of integration, moment of inertia of the element in the figure DIY equals differential IY. That would be the sort of what's the moment of inertia of this area. Well, this thing has a an area of dA of, let's see, it's going to have a height of, it's going to have a height of y, which is x to the 1/2, as a thickness of dx, right? And we have to multiply, so the moment of inertia of that little chunk there, our DIY is going to equal, whoops, stop that. There we go. Our DIY is going to equal x squared times our dA, right? And that's going to equal x squared times x to the 1/2 times dx. That's x to the 2.5 dx, so the answer is E. And dix equals, that's this dix is going to equal y, stop that, it's going to equal y cubed times 1/3 y cubed times dx. But y cubed, since y is x to the 1/2, y cubed equals x to the 3/2. So it's x to the 3/2 over 3 dx, so it's A. Okay, so these slides are up there if you want to keep playing around with this stuff. There's also a really good slide here which kind of summarizes all those things. Horizontal strip, vertical strip. You know, this is the formula for Ix. This is the formula for Iy. If you got a horizontal strip, if the base strip is on the y-axis, then you can do the Iy. If the base strip is on the x-axis, then you can do Ix. Okay, so that is something you want to put in your notes. Okay, so now, this is sort of the meaty part. This is going to be the basis of a pretty scary, this is like, uh, this is so painful, I don't like this. But anyway, we have to do it. The parallel axis theorem. So the parallel axis theorem is basically it's a way of, if you know the moment of inertia about a particular axis and you want to find the moment of inertia about another axis, it allows you to shift the axis and by doing an offset of your moment of inertia. Okay, and so here is the scenario. You've got these axes, x and y, and in this x and y frame, you know the centroid of A, this shape, right? And the centroid is going to be at x bar and y bar, right? But a lot of times, what we're interested in moment of inertia is the moment of inertia about the centroidal axis. But sometimes it's easier with composite bodies to find the moment of inertia about another axis. And then once you find the centroid, you could shift it to the centroidal axis and find out what its moment of inertia is about the centroidal axis. Okay, that's the rationale for why we're doing this. And so we might, once we find x bar and y bar, the centroid of A, we might want to know what's the moment of inertia about the x prime, y prime axis, which goes right through the centroid. And the point is, at some particular value, arbitrary value x and y, in the original coordinate system, there is a little dA chunk at some x and y, right? And as we were told, and we've been using this formula, the moment of inertia about the x-axis of this A shape is going to be the integral of all those dAs multiplied by y squared. But you can replace y if you're interested in another axis like the y prime x prime axis. You can replace y and be considered the sum of y bar plus y prime. So this is the location of this dA in the y prime axis, and this is the location of this dA in the x prime axis, right? All these things are kind of confusing. So y prime is how far this dA is from the centroidal x prime line, right? And if you want to reference that to the original axis, you got to add y bar back to it, right? So this distance here is y bar plus y prime, right? Because this distance here is y prime. That makes sense? Nothing up my sleeve. So that gives us the integral of y prime plus y bar squared dA. So you can square that, and what you're going to get is y prime squared plus 2 y prime y bar plus y bar squared times your dA. That was okay. So then you can group those terms and say, well, then that's going to be the integral of all of the y prime squares times dA plus 2 times y bar, that's your centroidal y bar, that's the location of that in the y-axis, times y prime dA plus y bar squared times the integral of all the dAs. Okay, well, we can inspect these, and if we think about it, what is this integral of y prime squared dA? What is that? Well, that's like the moment of inertia of this A shape about its centroidal axis in the centroidal x-axis. That's I x prime. We put this I bar over it. I think that I bar is kind of what they use for the centroidal moment of inertia. They put a bar over it for some reason. I don't know why, but I guess that's what they do. It's I bar x prime. That's the moment of inertia about the centroidal x prime axis, the axis that goes through the centroid of that shape. Interesting enough, the integral of y prime dA is really, that's the definition of the centroid in the y prime axis, but the centroid in the y prime axis should be 0 because that is actually right in the centroid. That axis is going right through the centroid, so the centroid y bar prime is going to be 0. Your axis just happens to be passing right through the centroid. That x prime axis is passing right through the centroid, so this is by definition going to be 0. And this is just A. So what you get is that Ix is the sum of the centroidal moment of inertia Ix prime. So Ix is the moment of inertia about the x-axis. I bar x prime is the moment of inertia about the centroidal axis, plus y bar squared times A, that's the centroid location, times the area. And likewise, Iy is going to be the same reasoning, is going to be I bar y prime plus x bar squared times A. So what is that again? So these are the moments of inertia in the some non-centroidal xy system. These guys are the centroidal moments. And these guys are the x bar, y bars are the centroid locations in x and y. And this theorem is going to help us in doing moments of inertia of composite bodies, because a lot of these composite bodies are going to be shifted with respect to their centroidal axis in some arbitrary location. We have to be able to, figure out what that contribution is going to be. And then when we're all done, we're going to shift that whole thing from some base axis to its own centroidal axis. And that takes a little bit of cogitation. So, for instance, the moment of inertia IT of a circular area with respect to a tangent to the circle. Here's an example. Well, we know I bar, that we're given this, you can find this in a lot of tables. I bar, that's the moment of inertia about the centroidal axis, is 1/4 pi r to the 4th. Well, if you were interested more in what's the moment of inertia of this thing about the tangent to it, you can use the parallel axis theorem and say, well, okay, IT, the tangential moment of inertia, is going to be the centroidal moment of inertia plus the distance to that tangent from the center of the circle squared times a. So that's going to equal 1/4 pi r to the 4th plus, well, that thing has a radius of r, so we're just going to say, okay, that's r squared. That's y bar squared times the area, which is just pi r squared. And if you add all that together, you're going to get 5/4 pi r to the 4th. So it's bigger, right? Because you're farther away from more material is farther away from the axis. The centroidal moment of inertia is going to be the smallest moment of inertia that body's going to have. You move away from that centroidal axis, you're going to get bigger. What about the moment of inertia of a triangle with respect to a centroidal axis? If we know the moment of inertia of a triangle with respect to the base of itself, the base of the triangle is 1/12 bh cubed. And we know that the distance to the centroidal axis is always like 1/3 of the height of the triangle. Then we know, again, according to the parallel axis theorem, that IAA prime, about this base, is going to equal BB prime, which is the centroidal. We'll put a bar across that. That's the centroidal moment of inertia of that triangle, plus y bar squared times A. So you can solve algebraically for IBB prime. I bar BB prime that means that's just going to be IAA prime minus y bar squared times A. And we know IAA prime, so that's going to equal 1/12 bh cubed minus, and then this y bar is this 1/3 h. This is our y bar is d, which is 1/3 h. That's into the centroid. We're going to square that, so minus 1/3 h squared times the area of that triangle, which is 1/2 times base times height. So that's going to give us bh cubed times 1/12 minus 1/18, which will end up telling us that our IBB prime is 1/36 times bh cubed. So we just used it going both ways, right? If you know the centroidal moment of inertia, you can find moment about some other axis that's offset from it. Or if you know the moment of inertia about that offset axis, you can find the centroidal moment of inertia. It's just kind of going back and forth by shifting. Essentially, you're shifting by y squared area. Okay, everybody so far so good? Hope you don't mind if I go a little bit long today. I'm going to move kind of fast if you can follow rapidly. Otherwise, these notes are all annotated online if you ever want to fill in any gaps in your notes. There are tables of moments of inertia of common area shapes, and they often provide the centroidal moment of inertia, and the moment of inertia may be about some base external to that body, so or tangential to the body. So those are nice. So Sometimes they do, sometimes they don't. But now with this tool, you can get them if you need them. And in a composite situation where you have some shape, again, this is a cross-sectional area of like a beam of some sort, you can break that shape up into parts and find the moment of inertia of each of those parts. But right, this hemisphere shape is going to have to be offset by a certain distance to get to its base or its centroid. So you have to factor that into account when you're doing the calculations of the contribution of each of these parts, right? That parallel axis theorem is going to come into play for these parts that are offset. The rectangle on the base on the axis is going to be fine as is, but then the circle is also offset a certain distance from its centroidal axis, so you have to shift it as well to get its true contribution to the moment of inertia of that whole body. And then when you're finished, you might want to just take, because we're sort of maybe going to reference it, it's sort of easy to reference everything to the x-axis, but then when we're finished, you know, the centroidal axis is maybe up here somewhere. We might want to shift the total answer back to its own centroidal axis of the whole body, again using the parallel axis theorem. So it's a multi-step process we're going to go through, and here we go. This one really helps to have alcohol handy when you're doing these. Just like, oh, I can't stand it anymore. Okay, I can do it. I can do this. So we're going to track this, and we're just going to find, in this case, we're going to find IX. IX, we're going to not even worry about it. And for each of these parts, we're going to break this thing into 4 parts, and we're going to have to find the area of the part, the centroid of that part, you know, offset of that centroid from the x-axis, the moment of inertia about the centroidal axis of that part, but ultimately, if we need to, if we're given that, but ultimately we're going to just reference everything to the x-axis and find the moment about the x-axis. So we don't have to do the centroidal moment if we don't need it. So the first part is a 3x3 square. Of course, there's a hole there. We're going to take a chunk out of that in a later section. But the area of that 3x3 square is going to be 9. And what is the y tilde of that 3x3 square? 1.5 feet. That's the distance to the center of that thing. Let me change the color here. That's easier to see. This distance is 1.5. That's the distance to the centroid of that square. And the moment of inertia, so our AI is, or I guess it's A1. Our A1 is 3 squared, which is 9. And our I1x is that formula that we derived yesterday, 1/3 times BH cubed, which is going to equal 1/3 times 3 times 3 cubed, which is going to give us 27 feet to the 4th. The area is feet to the 2nd. So that is a 2/7. Okay, we move on to part number 2, which is going to be the triangle. The area of part 2 is 1/2 times base times height, which is going to be 4.5 feet squared. And I2x is going to be 1/12 times BH cubed, which is going to be 1/12 times 3 times 3 cubed, which is going to be 6.75. So we enter A2 4.5. Oh, the height of the centroid for this thing is what? 1 foot. And again, IIX is 6.75. Okay, part number 3 is the semicircle shape. Starting with the area, A3 is 1/2 pi r squared, which is 1/2 times pi times 1.5 squared, that is the radius, which is 3.53. And now we have to find I bar 3 x prime. Now the x prime axis is the axis that goes through the centroid, which is 1.5 feet away from the x-axis. And according to one of the tables you can look up, you can find for a semicircle, you know, they give you these sort of things. Here's the x, here's the y-axis, that I, y, in this case, IY is the same as I bar y prime because it's the centroidal, it's going right through the center, is 1/8 pi r to the 4th. Well, when you have a semicircle that's oriented that way, the IY for that semicircle is the same as the IX prime for the one that's tilted vertically the way ours is, right? So you have to kind of be able to do those transformations as well. So this is going to be 1/8 pi r to the 4th. And that's going to be 1/8 pi times 1.5 to the 4th, which is 1.99. So we put the A, which is 3.53, the Y tilde thing, which is 1.5. And now we're going to put the 1.99 there. That's the centroidal moment of inertia of that circular half circle thing. But we really wanted to know what's the moment of inertia about that semicircle, about the tangent x-axis. It's tangent to it at the bottom. So we're going to have to use the parallel axis theorem to shift that, right? So we have to say, okay, well, that means I3x is going to be the moment I bar 3x prime, the centroidal moment, plus y bar 3 squared times A3, the area of that thing. So what we do is we take the 1.99 of the centroidal moment and add to it 1.5 squared times 3.53. And that'll give us 9.93 feet to the 4th, which we stick right there. Okay. That wraps up the third part. One more part is that circular hole. The circular hole is, has a radius of 1, and it is 1.5 away, as everything else is, from the x-axis. The y bar 4 is 1.5, so we can put that down here. The area is minus pi r squared, negative, minus pi times 1 squared. So that's minus 3.14. The centroidal moment of that circle is given to us as pi r to the 4th, or I'm sorry, 1/4 pi r to the 4th. We have to negate that because it is a hole. Minus 1/4 pi r to the 4th, and that gives us minus 1/4 pi times 1 to the 4th, which gives us minus 0.785. So that goes here. And then again, we got to do that shifting to find what's the moment of inertia about the x-axis. Okay, so then I 4x is going to equal I 4x prime bar, that's the centroidal, plus y 4 squared times a4. And that's going to equal minus 0.785 plus 1.5 squared times negative 3.14, which is going to give us minus 7.85. Okay, that is the moment of inertia that's been removed by taking that hole out of it. Okay, so that's the hard work. Now we have to find the total IX. That's pretty easy. The total IX is just the sum of all of those. Of all the IXs. And that works out to be 35.83. But, and my understanding is, I'm not a mechanical engineer, but I think what really happens, if this thing actually is subjected to buckling, it's going to bend around its centroidal axis, not around some external tangential axis for that beam. So we would be more interested in finding the moment of inertia about its centroidal neutral axis, x prime. And we found out what that was in an earlier lecture when we did the same thing for centroid. We found the centroid of this thing already last week. So IX is IX prime bar plus Y bar squared times A. We just have to actually move our answer by shifting the x-axis towards the centroid, right? So, and ix, which we found, is going to be ix bar prime, blah, blah, blah. So he's going to solve for ix prime bar. And that's going to equal 35.83. That was all the ix's that we added together, minus the distance to the centroid. We found this was, this is on the handout here. Oh, and also this is the sum of all the areas. Oops. 13.89. 1.34 is the height of the centroid x prime axis from x. So 35.83 minus 1.34 squared times 13.89. And that tells us that the ix prime bar of that shape is 10.89 feet to the fourth. So that's basically it. It's kind of a weird way to end the lectures the semester, but that's sort of where we sort of end this class. I'll take any homework if you have it. There you got it. That was fast. I'm not sure that is the answer that you should put on there. You might have to do this again. You usually want to say something like, I've learned it through independent study already, or something like that. Well, because I was supposed to maybe as long as I sign off on it, it's okay. You only have a red pen. You have a non-red. Let me know if you have any issues. Actually, I think it's the other way around. Oh no, I gave you the right one. Yeah, you get the pink one.